right, let's get started. We have like a lot of material to cover. Hopefully, I'm not gonna sleep. So today we're gonna be talking about PlayStation and Lucene. Apparently, PlayStation uses Lucene behind the scene. And let's start with me, Alex. Here's my PlayStation Network ID. So I'm principal software engineer working for Sony interactive entertainment company behind PlayStation services, actually. And then here's my very high-level career path. Started with outsourcing a bunch of projects, did a little bit of everything, then worked at Google for a little bit, then went to a company called Betfair. It was like a startup in the United States, well-established company in UK. Didn't work well. Everyone was laid off after like 9 months, and here I am at PlayStation now. So, and that's it for me. Agenda. So today we'll talk about quick PlayStation overview. I will not spend a lot of time on this topic. So then we'll move to like search at PlayStation. It will be another very brief introduction what we do. Then I'll talk about our first system. The first system we built that does this thing, like 200,000 documents per second. It's built for PlayStation Store. Then I'll talk about another project called Friends Finder, and an epic journey. Originally, I want to call it epic fail, but then like journey sounds like better. And then finally, we'll talk about this system that was born on top of Friends Finder as a result of Friends Finder's epic journey. So PlayStation is very big. It's growing very fast. PlayStation Network is expanding. 65 million monthly active users, hundreds of millions of active users. It's not tied to the device. Before it was. Right now, PlayStation Network spans across. It's in your TVs. It's online. It's like everywhere. There's PlayStation Music, PlayStation Video. Talking about just devices, 40 million of new gen. Like old gen is like 100 million, I think. The Vitas, it's a lot, plus phones. And a lot of services. Some of them, PlayStation Network, right? It's a core one. PlayStation Store, it's a game store for PlayStation, literally. PlayStation Video, it's like Hulu. It's almost like a Voodoo experience or Amazon when you can buy videos and stream them. We have it. PlayStation View, I don't know if you heard about this one. That's like next-gen online television, like Comcast, but on demand and without surprises. Like every time I get a bill from Comcast, like, oh, what just happened? Why do I need to pay like 150 bucks? So this supposedly fixes this problem. PlayStation Music, I mentioned it. And finally, interesting one, PlayStation Now, it's online game streaming, right? We have data centers with devices, so you can play a game on TV. We're gonna just stream it to you. Very low latency, very nice experience. That's about PlayStation. So, and then, of course, on such a big platform, we do have search. You cannot live without search these days. Some examples are PlayStation Store search. You want to buy something, you just type your game, punched it, you just get some products as a result. You click on it, you can buy it. Another one, that's a friends search, friends finder per se, right? You can find users on the platform. Another one is, we call it user-generated content. When people interact with the platform, they upload videos, they stream videos, images, a lot of things. Everything ends up in this system, and then people can, users can go there and see what's trending, what to watch, what to enjoy. And then if you think about it, even PlayStation Store, it's kind of powered by search. Even though it looks like static, like you have categories, but behind it, it's a search engine, of course, right? Because everything should be dynamic these days. And that's it with introduction. I told you very fast, not a lot of advertisement. And this section, so PlayStation Store. What's that? That's a big online store for PlayStation. To give you an idea, right? That's how much money it's generating. I will not compare it to some unicorns from Bay Area, but you get an idea, right? The growth pattern is very interesting. More than Nintendo, right? Someone wrote it on the internet. That's it. And I'm not talking about everything at PlayStation, just PlayStation Store. And then not just e-commerce, it's more, it's multiple services. If you think about it, Google started with a search, we started with kind of the store. And now we just go in everywhere. Search use cases. Simple game of video search. Nothing is interesting here. It's just Solr. And of course, we're not indexing a lot of documents in the Solr because there are not enough games in the world. I think even Baidu does 100,050 pages per second, right? So of course we cannot be at this scale. There's no games. And there's another piece of the platform. It's user game video library. And then I will be talking about this system. Internally, it's powered by Lucene and Cassandra. And what it does, it gives users ability to search inside their own context or their own world, let's say. It's not kind of exposed to the user. You cannot go and do it. It's mostly built for backend services, right? So you'll see how it works. So what were the challenges that led to the birth of this giant? So we're not Amazon. So when you buy something, you want to use it right away. So if you think about Amazon, when you do this one button purchase, it's instant, like boom. If you go and try to rent a video from them, it's not that fast, like 5 seconds, it's like spinning and spinning and spinning. And you might think, why is that? Maybe because when you do an order on Amazon, they have 5 hours or maybe 5 days to fulfill your order. If something goes wrong with your credit card or something broken, they just roll it back. It's fine. Not the case for us. You bought your game, you want to stream it, download it right away. Same with videos. Also, every transaction on the system, it's not just sitting there, right? It's not just something you use sometimes. What did I order 5 months ago? Let me search. It's not like this. If you think about it, we have a service called PlayStation Plus. If you can play multiplayer only if you have PlayStation Plus service. So it's kind of an entitlement internally. So you're entitled to use the service, which means every time you want to play something, right, to start the game, there's a check that's going on. And there are multiple checks, and it's all real time, and it should be very, very fast. Otherwise, people will be very unhappy. Which means all of it kind of leads to several ideas. System should be highly available, right? There's no doubt. It cannot go down. It should be fast. Because it's a backend system, it's behind multiple layers of different microservices, and latency, it adds up very fast. It should be very, very fast, almost immediate response. It should be easy to scale. We are growing very fast. We started PlayStation 4 launch. We went from 0 users, it was brand new software, to 2 million users in one day, right? And since then, we were adding like 1 million or 2 million users per month. Right, so original design was supposed to be scalable. And it should be, that's mine, addition, launch and forget, because I don't really like to be on call all the time and be like supporting all the systems. I don't like to be in the situation when you launch something, it broke, you fixed it, it broke again, you find like workaround, you patched it broke later, like no. I want to deploy it and then let it live its own life. If there's feature request, fix it, do it, but then don't deal with this system all the time. The problem, back then, 3 years ago, 4 years ago, we had this legacy system that used well-known relational database. It was had been handling our transactions. Because PlayStation Network by itself, it's like 10 years company, I think. And it's state-of-the-art software that doesn't scale well. Unfortunately. And then we also wanted to allow clients to run all the queries without consulting with a bunch of DBAs all the time. We know how it works in like relational world. You need to consult with someone to make sure your query will not like lock up all the tables in your cluster. I saw it happening before. So yeah, I didn't want to be in this place. I wanted to deploy something and then tell client, hey guys, here's core language. You can abuse it, do whatever you want. Don't talk to me, please. Like, talk to me if it breaks. And at that point, sharding sounded like a pain. We had people on the team with experience in sharding. You can watch videos from Uber when they talk about their ping pong with Postgres and MySQL, how they were switching and then built own sharding system at the end, which looks like Cassandra. It's kind of fun to do, but maybe not in 3 months. And another requirement, multiple regions should be easy, and it should be active-active, no master-slave stuff, right? It should be deployed everywhere, and it should work just flawlessly without like any headaches. That's a problem. Solution, if you go online and search, people usually, oh yeah, you have relational DB on one side, your client on another, just slap NoSQL database, done. Unfortunately, it's not easy to do it. For user-facing traffic, when you have a lot of queries, actually it's not easy in general. You cannot just replace relational database with Cassandra. I'm very sorry. If anyone thinks it's easy, you just, based on some presentation, it's not. Presentations, it's not. It's a lot of work and thought and refactoring. So, and here's why. So here's simple digital store model, very simplified. If you're not familiar with e-commerce, no worries. So we have a user at the very left, and then user has entitlements. You're entitled to use something. It's like a flag that you bought something. And everything behind the thing, behind it is kind of metadata. You see a lot of many-to-many relations. And then it's just very simple, very several tables. In reality, it's many more tables, and you have another like hundreds tables, which are like usually involved. So we had all of this. We had 4 months to come up with something that's going to scale for PlayStation 4 launch. And we were thinking, all right, what we're going to do? What's actually doable? Sharding, like Couchbase, Cassandra, Solr, what should we do? So we thought about it, and then we were thinking, because we didn't have user traffic yet, right? So we're thinking that probably users will be, a lot of load will come from user-centric activities, which means user will be interacting with own content, not like running count star from some table, group by something. So it means that you can actually somehow, if you go, you can shard, of course, or you can go really extreme with sharding. And then also it means that system will not need to join things, or at least joins will be minimized, or at least we can make joins minimal. And then we decided, let's denormalize. So do you remember the store model? So it's kind of a JSON representation of it with some data in it, right? So that's the way you usually do stuff with NoSQL. You take your relations, you put it in one huge document, JSON or something, then you store it. And that's how we came up with the first model. That's Cassandra model, but it's very similar to any other NoSQL databases. You have account, you have JSON, and you have a bunch of storage JSONs. And now it's cool. It's horizontally scales as long as NoSQL scales. And it's backed by Cassandra. Of course it scales, right? No doubts here. There's some rudimentary transactions. Even if you write same row, everything is transactional in this one write, right? So, and then because everything lives inside user's bucket, everything for user is transactional, if you do it right, of course, for one write. And then really fast reads, no joins. You just go inside this database, get the thing, and get out. Done. Some problems. How do we move purchases from one system to another? And that's actually an easy problem to solve, by the way. There are notifications. You can come up with some way of pinning the system with some revision ID, percent, and saying like anything new, multiple ways. Another one, updates to shared data. What I mean by shared data, let's say we have Call of Duty, got purchased by 10 million users. And then later, publisher says, oh, there's a typo in the name, right? So we want to, right now, just go and update all the 10 million users. Relational database, easy. You just write one thing, next word comes, joins, done. Not with this schema, right? The JSON, they separate locations. And then, yeah, queries. We still didn't fix the problem with queries. So we were thinking, what does client want? Search, sort, filter. I mean, usually a very simple thing. What can we do? We can use some kind of secondary index black magic, right? Some databases support it, like Cassandra, Couchbase, they have it. And also just pull everything from the user's bucket in memory, just do the sorting in memory, and then return the result. Or we can use Solr. Why not? We had Solr deployment for PlayStation Store. And then, I'm not sure. I mean, we brainstormed it. We did some prototypes. We didn't like it. There's several questions. How can you do those user-level queries? And how can you make them really fast? Data is both high cardinality and low cardinality. You have things like timestamps all over the place, and you have things like title names or like even object types, right? And you want to query by all of it. You want to query for user X, give me please all the games which he played or she in the last 25 days sorted by something, right? Stuff like that. And then, yeah, indexing relations is, how do you do it? We create a document in a like NoSQL way and then index everything or index a relation. And then, honestly, Solar was built for different use case, right? The use case, a website, a lot of data, you index and you go, type something, and here you go, here's your hits, right? So, another thing, Solar comes with additional overhead. At this point of time, we were running Solar 3.6, I believe. It wasn't really, Solar Cloud wasn't around, but even with Solar Cloud, there is Zookeeper. Now you need to deal with Zookeeper. And I'm personally not happy with Zookeeper. I actually know one security company which banned Zookeeper. They said, no Zookeepers. They even run Spark. They built on automation for it. And then because we had interesting situations with it in production, and I will not use Zookeeper for I would not use it for multi-regional replication, period. So given all of it, what can we do? We can actually create an index ourselves. And then from a software engineering perspective, writing own indexer sounds like a lot of fun. It's actually when people can apply what they learned in CS 101 class, right, back at university, finally. But someone already had all this fun and just came up with Lucene. So we said, like, hey, let's use Lucene. Why not? So we took our schema and we just slapped Lucene on top of it, right? That's all we did. So you see this version field. I'll talk about it later. So now we can search anything inside this user bucket. Easy. Index is very small, so it's extremely fast. Also, we never update the index. Index is always rebuilt from scratch, so there's no compactions. It's discarded. Update comes, rebuild whole thing, remove old one, new one is ready to go. Size is usually, I never saw indexes for this use case bigger than like 200 kilobytes compressed. They're very small. And then, but then the same problem stays. Now we kind of need to pull this index in memory. And then, as you know, there's microservices. This is a stateless design per se. When folks say, if you write in a software, you need to rely on the state in your database because someone who created the database knew what they were doing, and you don't know what you're doing, and it's really hard to maintain your state. So what you're going to do is just, do pass-through API, go to the database, fetch the object, and return. And it's stateless design. Stateless database has state, right? I hope everyone understands it. There's no stateless designs unless you do 1+1 kind of computations. So, and then another problem was, what happens if two servers doing updates, right? If they're all stateless and then verify each other, that can happen. So, one of the ideas, distributed cache. Why not? It's nice to keep things as close to your service as possible, right? It's good. Low latency is always good. And something that do fast reads. And then we have a lot of RAMs these days. We, on Amazon, right now, we can go up to almost 2 terabytes of RAM with the X1 family. Back in these days, I think the biggest box was 256 gigs, but still a lot. So we can have something like this. Memcached, Redis, AirSpike. You might ask me, oh, but you said you're using NoSQL. And all NoSQL benchmarks, every single benchmark of every single database proves that it's the fastest thing on the planet and beats anything else, caches included. So we used Cassandra as a cache. We're still using it. And then Redis is faster. And Memcached is faster. So, right? But even if you do it, there's still network penalty. You need to go to the place and stream those bytes. And if we're talking about tens of thousands of requests per second, and each index size is 200 kilobytes or 50 kilobytes, it all adds up very fast, right? It's like bandwidth is not infinite. And then we were thinking, like, what if there's a soft state pattern. I think it's known in hardware. If you go to Wikipedia, you will not find a lot. It's like very empty page. So the idea was you can have a state, but it should be just state for performance purposes, right? You can discard it anytime, and if it's discarded or updated, you should be able to just continue. That was the idea. So we were thinking, what if we do it, right? So we put cache right inside our microservice. And then, because if you put cache inside your Java application, you're going to deal with garbage collection. We said, oh, wow, we can use off-heap cache, and Cache has this interesting project. Then why not? Then another problem with soft state, requests from the same user should land on the same server. So you have kind of a leader problem, but not actually, because you don't have replica problem. And the idea is, if your leader dies, you just forget about it and switch load to another server. And another server needs to have all the required information to restore the soft state and continue serving the request. So changes to this state should be replicated to some storage. In our case, it's Cassandra, right? It's Cassandra, and Cassandra should be solid in this use case, like in any other use case. If Cassandra is unstable, it's the end of the, that's it, right? And then version column, the one that I put in the schema, it had some really simple information: Lucene version, index version, and also by index version, I mean what's the schema version of the index, and also version of actual index. And then this field was used to figure out if index in a memory state is stale or not, right? So for every request, go to Cassandra first or to any distributed cache, check this ID, compare what's in memory. If they match, you're good to go. If they don't match, then somehow it got stale. It should not happen because only one server serves requests for the same user. But if we scaling up or scaling down, it can shift, right? And it's more like protection mechanism. And yeah, if server goes down, session automatically moves. And it's easier to scale up microservices in database. Database takes hours, especially if you have terabytes of data. Microservices take, last time I checked on Amazon, 2 minutes. Like, right, you can double your capacity or triple or quadruple. All you need is to make sure Amazon has enough instances, because sometimes they don't. So they just tell you, I'm sorry. We need to buy some hardware. So in other words, that's how the system looked like. NoSQL database, applications talking to it. Each app has a bunch of those buckets, Lucene indices, and then there's some kind of self-awareness. And I'll talk about it, how we actually did it originally. Here it looks like there's consistent hashing involved, but you don't have to do it. And gossiping, you don't have to do it, actually. There's an easier way if you're on Amazon. If you're not, there's also an easy way. And then we did modify Lucene a little bit, actually. Surprisingly, I mean, there's always a way to do it much better, but the things that went in production originally had two simple fixes: RAM file and RAM directory. We just added implement serializable. That's it. And then, of course, we had to just do writable RAM directory, writable RAM input stream, and output stream, and RAM file, because they all kind of work together. But that's it, all the changes. Routing, simple. On Amazon, we have a thing called Elastic Load Balancer. It has sticky session, but it only works with clients, because the idea is when a request goes back, it returns sticky session to the client, and the assumption is that browser will keep this cookie, and when it sends requests back, it kind of gives cookie back. I talked to Amazon, like, hey guys, can I somehow maybe do it server side? When my service calls another service, I want to pass something. They said no. So we're like, okay, we just get the cookie from the request and just store it in key value. And when we need to call it back, we just pull it from the storage and then attach it to the request. And then it actually works pretty well. There are like some corner cases, right? When two requests come in the first time and user is not pre-warmed, they both will go through. But it's OK, because worst case scenario, both servers will do work. And then, right, at some point, load will switch to one server and another one will evict index from memory. So what if this data changes? You know, this cross-user data like title name. Products could be renamed, game image just got updated, or package URL where game lives was changed, so you want to move it. What if it happens? So Einstein solved this problem 100 years ago, actually, for us. And then I think that's where idea of eventual consistency got born. You remember this one, two lightings striking, one user sees events in different order. So if two events happened, two different games got updated. You don't have to update all the users in the same time. I mean, in our use case, maybe you do, right? I don't. It means that I can do a very simple solution. It's based on eventual consistency model, but not like on database level. It's a higher. You just find literally all the users and slowly tell them, your data is stale, please update your index. That's it. So simple solution, reverse lookup table to find all the affected users. We did it in Cassandra. We did it in memory using Samza and Kafka. It can work really well. So like a bunch of ways to do it. Actually, you can do it even in SQL. And then when something changes, just find all the users and lazily reindex. Or you can do just reindex. But I mean, reindexing right away 10 million or 50 million users might not be a good idea. We do it lazily when user comes online, because users usually come online in certain times. We have this, because users usually either in US or in Europe or in Japan, they spread across the world. So not everyone is online all the time. So how about stats? So currently, the system has tens of billions of documents. It's not just what user bought. After system got deployed, people was excited, like, oh, I can also add additional things. What user played, what users saw, and then it just exploded. Average API latency is 10 milliseconds. It's load balancer latency, and there are a lot of things involved. Security checks, authentication, authorization, Cassandra round trips. Search latency is in microseconds. Once index is in memory, it's like almost free. Search is very free. And then hundreds of thousands of documents are indexed per second during spikes. Not every. Usually it's like maybe 50-ish, but sometimes when there's huge massive update or huge big title goes out and people just buying it like crazy, and then someone fixes some problem, and then those changes adds up, and then system goes and indexes a lot of things in memory. And most importantly, no major incident in production, right? No zookeeper, right? So no zookeeper, no problem. So let's talk about another next system. It's called Friends Finder. After after we went through PlayStation 4 launch and things come down, new features started to come, right? As always. And then we were asked to add this thing, right? We wanted to find all the users on a platform, right, to give users ability to do it. This feature got born from an internal hackathon. Someone presented it. Executives loved it. And then here we go, we're developing it. There's some catch, right? It should respect privacy setting. If I don't want to be searchable, I should be able to opt out, plus additional things. Also, want to recommend new friends you may know, and we wanted to do it better than LinkedIn. Have you ever saw situation when there are two similar faces in your feed, same person recommended twice? I actually have this screenshot, but I thought it will not be appropriate to put it on my slides because I don't know, maybe people don't want to, right? I don't know those people, but it happens with some you may know systems. And then results, when you do a search, results should be ordered in the following order: your direct friends, your friends of friends, the ones that are searchable, and then everyone else. So this friends of friends is interesting if you think about number of possible friends of friends out there. And then it should be, project was supposed to be done very fast with very small team. So we figured out we can use Solr to index everyone. So it will be like platform-wide search, same as PlayStation Store. Put all the names in the Solr, all the metadata that should be searchable. Then you run your query, you're done. For this one, we used actually, because it's a newer software, it uses Solr Cloud, it uses Solr 5. And then we decided to use the same idea we did for PlayStation Store with personal indices. So we can sort by distance. We can sort by other related fields. Who do I play with often? Facebook friends, right? You can do a really rich metadata. And then you may know it's technically just another search. You just want to search, say, give me 50 or 10 friends, sorted by number of common friends, done. works. And then, of course, you need to have some notification system in place so you can rebuild those indices when people create connections. And that system design, we have social network, we had this friends finder, so there's change, it fires it to the queue, right? The indexer gets the change, writes it to Solar Cloud only if it's a user or name change or privacy update, and also it does personal index, writes it to Cassandra, and then when friend finder searches and goes to both places, gets both results, merges them, presents it to the user. Simple. How did it do? Solar was fine, quite fine, except Zookeeper gave us some troubles in production. Personalized part was not so fine. What happened? So each change in friendship required reindexing a lot of users, especially for indexing friends of friends. This possible graph is like growing. You have 20 friends, they have 20 friends, we have 400 users. And that's just with 20 friends. Privacy settings updates, same problem. So in NoSQL, we used Cassandra, uses SS tables approach. So if you remember, with SS tables, you cannot modify it. Write goes to a new SS table, and then there is procedure called compaction. So later, in some point, database reads both files, compacts them together, writes the result. So space is not released right away, and if you write a lot, your space can just go up and up and up. And then, yeah, as a result, data size was growing much faster. So we decided to take an action. So do you know, actually, anyone knows how this fast growth actually called in physics? No? It's called explosion, right? So that's what happened. We decided that, well, with this growth pattern, we need to do something. And we ended up with another beast that we needed to tame and do it really fast. So we got some insights. You may know was put in a lot of load because you may know recommendations was right in the face of the users when they will log in. During the login, you go on PlayStation 4, there's this activity feed, like PlayStation feed, and you may know was right there. Bunch of calls. So both update indexing and lazy indexing, concepts we use in PlayStation Store, didn't really help. And what we also found that users usually don't search frequently, but when they do search, they usually interact for some time because they explore, they search for someone, so they could misspell, and then there's this process. So we took some actions. Cached, you may know. Learning it doesn't help, all right? And then back to the drawing board. And then another crazy idea was born. So the idea was knowing all of it, that users searches for some time, and we also analyzed all those search hits, and so how big a search session, we use Spark for this one. We kind of, after we crunched the data, we're like, well, what if we do ephemeral indices? What if we just create an index on demand, keep it during the search session, and then just discard it at the end? And we can use same code. It's very similar. We just don't go to the database. And we always reindex when it's a cache maze. And we came up with more boxes. So it's almost the same boxes, by the way. Social network change goes to indexer, which only writes to Solar. All right? Then we have this personalized search microservice. When Friends Finder calls it, personalized search microservice calls social network and asks for all your friends and friends of friends and all related metadata. Once it gets it, it also subscribes to this queue to make sure index is not stale. And that's it. Profit, right? Is it fixed yet? Not really. We found that indexing should be extremely fast, right? Because we indexing almost on demand. And then when we looked inside what's going in Profiler, we found that significant time and resources I spent on actually pulling your friends and friends of friends and all the metadata. And we just talked about the soft state. But before we had the soft state when we were doing sticky, and then in this case, how can you do soft state with all the users' metadata? And we did some math, right? We have hundreds of millions of users, but number of active users is not that big. So let's say searchable metadata is 200 bytes compressed. How much memory do we need? Not much, 18 gigs. My math might be wrong, but I think originally we had less metadata, and we came up with something like 6, 7, 8 gigs. So it's doable. And we thought, what if we do something like that? We have application memory, we have Java heap, let's say it's 8 gigs, then we have off-heap space. And then there are already Lucene indices living there. So we just reduce space, and we put all accounts info, accounts of information of everyone on the system in this space. Also, on Amazon, surprisingly, each instance, like new family, R3s especially, even C3s, I think, they all have SSDs. And because we will use stateless design, we don't use them. They just sit there idle, right? You have 100 gigs, 200 gigs on the box. Those gigs doing nothing, actually. So we thought, oh, we can utilize it for spillover. Why not? It's really fast. It's still faster than going to Redis, actually, if you just do a fast lookup. Will it work? Technically, it can, right? As I mentioned before, a lot of RAM is available. Right now, there's a new family. It's so beefy, you can probably put all the world in there. And yeah, the only catch, now we need to propagate changes, because if user changes name and changes privacy, all those things should be notified, which is also problems that's solvable, and it's not that hard to solve, actually. There are queues on Amazon, there is Kafka. So it sounds like it can work. And it did work. So here's some stats. It's like ordinary day. I think it was Sunday. So you can see on the left side, it's number of documents indexed per second. So it was like on a high level, it was around, what was that actually? 809-ish, and there was a spike that went through 1 million. Sometimes it depends on the day, actually. Closer to Christmas, it's higher. Right now, it's lower. And then index speed is between 100 and 200 milliseconds. Spike, yes, it went up, but usually at 150 to do indexing. And because data is usually kept in memory, when it's only cold request, right? When cache is warmed, its latency goes down to milliseconds. And that's number of servers. It's not like 18 right now. When I did the screenshot, it's 24. And it's 24 because we actually add capacity and remove capacity. Operations also play in a lot with different instance types on Amazon. Sometimes we deploy a new cluster with a different size just to see how it behaves. At this time, it's 24. So each server was indexing like around 40,000 documents per second. Some learnings. Actually, a lot. Right? You can do wonders if you're desperate enough. Worked before doesn't mean, it's a pretty obvious one, common sense. Worked before doesn't mean it's going to work this time. And then Lucene is extremely fast when index is small. It's discarded. It's extremely fast. And also, it's open source, so you can go and see what's going wrong, and you can change it if you want. Well, that's cool. Just recompile it and plug it in. And then it can be applied to the use cases that don't look like search at all, right? Our use case, especially the first one, didn't look like search. Even when it got proposed, people were like, well, Lucene, for this thing, that's not going to work. And it worked. And then when we thought that same approach is going to work for something that is search-related, it didn't work. So we had to do a lot of changes. And probably one more learning is, it's really nice when engineers know internals of the libraries they use, systems they use. It helps a lot. And it actually makes everyone's life easier. So encourage everyone, even if you just operator maintaining Solar, just go into code and learn how does it work and why it does what it does, right? And that's it, actually. Oh, yeah, by the way, RAM, you can beat it, right? Pretty obvious. That's it.